Hello everyone, I am Vamshi from EC department. My 80 Tech Talk topic is about low probability of detection, communication, opportunities and challenges. Abstract. LPD communication has recently emerged as a new transmission technology to address privacy and security in wireless networks. Recent studies have established the fundamental limits of LPD communication in terms of the amount of information that can be conveyed from a transmitter to a receiver subject to a constraint on a warden's detection error probability. The established information theoretic metric enables analytical studies on the design and performance of LPD communication under various channel conditions. In this article, we present the key features of LPD communications and discuss various important design considerations. First, we clarify the differences between LPD communications and well-known physical layer security. Then, from an information theoretic point of view, we discuss the optimal signaling strategies for transmitting the message carrying signal and artificial noise signal for LPD communications. Finally, we identify the key challenges in the design of practical LPD communication system and point out future research directions in this context. In this article, we represent the key features of LPD communications and discuss various channel conditions. In this important design considerations, first we clarify the differences between LPD communications and well-known physical layer security. Then, from an information theoretic point of view, we discuss the optimal signaling strategies for transmitting the message carrying signal and artificial noise signal for LPD communication. Finally, we identify the key challenges in the design of practical LPD communication systems and point of future research direction in this context. This article provides guidelines for designing practical LPD communication strategies in wireless systems and networks. Introduction. As fifth generation 5G wireless networks together with the Internet of Things are brought to reality, people and organizations become more independent on wireless devices to share secure and private information. Example, location or psychological information for health. An impediment to widespread adoption of these technologies are people's concern about security and privacy of wireless communications. For example, the exposure of an embedded medical device's transmission may indicate the sickness of a user and may also disclose the user's locations. Either of these may be a violation of privacy. To guarantee strong security of privacy, it is often not sufficient to only protect the content of communications, but it is also required to hide the very existence of wireless transmission. Hiding wireless transmissions may also be explicitly decided by government and military bodies. However, there is a lack of understanding on the performance limit and enabling technologies for hiding. Recent research on LPD communication aims at the potential integration of LPD communication techniques into current and future wireless network. Example, 5G wireless network and IoT to protect the privacy and security of server users. LPD communication technology is also critical to government and military bodies. For instance, with increasing cybercrime throughout the world, police or military units desire to detect communications between any potential cyber criminals and the presence even without the content of such communications may offer sufficient alarm for government bodies or military units to take action. Research in this area will provide a thorough understanding of LPD communications, which can enable the government to enhance national security through foreseeing any future fortunate or devastating impact of this technology on our national cyber security. Understand how to regulate the use of this new technology in future wireless communication. LPD communication technology has drawn significant research interest since 2013. Existing research in this field can be broadly categorized into three main directions with overlap. The first category focus on characterizing the performance limits of LPD communications, which aims to disclose the amount of information that can be conveyed with a negligible detection probability. The second one is on encoding schemes to achieve LPD communications, focusing on constructing practical encoding schemes and characterizing the required key size in order to achieve the LPD communication limits. The third category on LPD communication performance enhancements targets examining possibilities and developing techniques to improve LPD communication performances in realistic environments. Although the limited preliminary work in each category has provided with some initial understanding of LPD communication, many challenges, problems, and issues have not been addressed. Against this background, in this article, we first discuss the fundamental features of LPD communications and provide and a comparison with a closely related technology. Physical layer security. We then highlight some existing research result of LPD communication, further identifying significant challenging problems and issues in designing practical LPD communication systems, and finally provide our recommendations on future research directions in LPD communications. The figure shows a wireless LPD communication scenario where a prisoner alias tries to send critical information to a receiver Bob, subject to a negligible probability of being detected by the guard William. Existing main results on LPD communication and key differences between LPD communication and physical layer security. In this section, we first present a motivation scenario for LPD communication and some main conclusions in this research directions. Then we clarify the difference between LPD communications and physical layer security. A prisoner's LPD communication problem and spread spectrum. In wireless network, the LPD communication problem can be described using pioneer's communication scenario as shown in figure 1, where a pioneer alias intends to transmit critical information to a receiver Bob subject to a negligible probability of being detected by the ground Willie. In this scenario, the guard does not care what alias transmits, but he would confiscate alias phones if he detects her transmission. As such, from Willie's perspective, he is going to detect whether Alice's wireless transmission occurs or not, which is a binary detection problem. Meanwhile, from Alice's perspective, she has to hide her wireless communication to Bob in order to avoid losing her phone. Spread spectrum was actually used widely to hide military wireless communication during World War II. However, the fundamental performance limit of spread spectrum in terms of the amount of information that can be transferred convertly with a certain hiddeness level was unknown. Without such limit analysis, we cannot answer many questions with regard to the fundamental performance limit of spread spectrum in terms of the achieved covertness. Square roots and its extension in LPD communication. The square root law was derived by considering additive white Gaussian noise channels for both Bob and Willie, which states that no more than n bits can be conveyed reliable from alias to Bob in n channel uses, while lower bounding Willie's detection error probability of this transmission being no less than a specific value e. After the scaling constant of the amount of convert information with respect to n was characterized for a discrete memoryless channel and the AWGN channel. The achievability of the square root law normally requires pre-shared scenarios between Alice and Bob prior to Alice transmissions. For DMCS, this key size was shown to be on the order of n to achieve the square root law regardless of the quality of the channel. In addition, this pre-shared secret was proven to be unnecessary when the channel quality from Alice to Bob is higher than the from Alice to Willie. The figure 2 shows system models of a low probability of detection, LPD communication, physical layer security. LPD communication with the aid of artificial noise. The performance of LPD communication can be effectively improved by the transmission strategies with the aid of artificial noise. It was shown that LPD communication with n bits over n channel uses could be achieved when uniformly distributed is present to help the transmitter analyze in AM, AWGN and block fading channel. Besides external jammers and transmitted by a full duplex receivers, Bob can enable LPD communication and significantly improve its performances. Especially, it was shown that the transmission of AN with varying power, although causing self-interference at Bob, provides the opportunity of achieving covertness without other uncertainties. Differences between LPD communication and physical layer security. Researchers from the physical layer security community who started to see LPD communications as a closely related technology for achieving security. Nevertheless, there are fundamental differences between LPD communication and physical layer security. To clarify these differences, we first present their fundamental features as illustrated in figure 2. From this figure, we can see that the main difference between LPD communication and physical layer security is in the nature of the malicious user. The malicious user in LPD communications is the warden Willie, who cares whether the transmitted alias transmits information to the legitimate receive Bob. Multi-hop communication. The low power nature of LPD communication significantly restricts the communication range. Therefore, multi-hop communication is essential in many applications of LPD communications where the end-to-end communication distance is large. In figure 5, we show an application scenario of multi-hop LPD communications where a single hop communication cannot achieve enough covertness. This is due to the fact that the communication distance is large and thus the transmitted power should be high to support such long distance communication. In this construct, another feature research direction is to design practical transmission strategies to achieve acceptable scaling behavior of LPD communication performance with respect to the density of legitimate transceivers or wardens, taking into account the realistic spatial characteristics of wireless channels.